Hello Doctor and my fellow classmates. Today we are presenting our group assignment for Engineering Mathematics 1 and the topic is functions that related to biochemical engineering. Before we get into these slides, I would like to introduce my group members. I'm Surendran Nathan, matrix number 217012, and here we have Trisha Devendran, matrix number 217120, Geethan Shanmugam, matrix number 215232, Nishantini Kumar, matrix number 216029, and finally Chitya Bashni Jitnamurthy, matrix number 215362. The theory that we chose from biochemical engineering is sterilization. Now Geethan Shanmugam will continue the presentation on what is sterilization and the purpose of the theory.
Hello everyone. First of all, I would like to explain about what is sterilization. Sterilization is the process of inactivating or removing all the viable microorganisms from the substance or the surface. Sterilization is one of the most important operations which differentiate a biochemical process from a chemical process. Sterilization provides contamination-free environment. These are some examples of sterilizer. Now, I would like to explain about what are the effects of contaminant. Medium would be consumed unnecessarily to support the growth of contaminating organisms. Contaminated product may outweigh the desired product, may contaminate the final product. The contaminated product may interfere with the recovery of the desired product. Unsterile air in aerobic fermentation can spoil the fermentation product. In this slide, we are going to see sterilization of the medium to avoid contaminating organisms which may use the nutrients in the medium, change the chemical structure of the medium, change the pH to create more foam, produce other products, and convert, degrade, or destroy desired product. And finally, in this slide, we are going to look at the methods to avoid contamination in fermentation process. There are a lot of methods to avoid contamination. First of all, sterilization of medium, employing pure inoculum, sterilization of fermenter, then sterilization on air, sterilizing the pipes, valve, and vents, sterilization of material to be added to the fermenter, disinfecting the fermenter with a non-toxic disinfectant, maintaining aseptic condition in the fermenter during fermentation, and finally maintaining optimum pH which discourages the growth of undesired organisms.
Kinetics of thermal death of microorganisms. Practical consideration. Basically, not all the organisms have identical death kinetics. Individuals within a population of the same organism may have different response. For example, heat is used to kill contaminant microorganisms and spores that present in a liquid nutrient medium. The destruction of microorganisms by heat means loss of viability of these microorganisms and spores. The thermal death of microorganisms follow first-order kinetics given by the equation 1, which is negative dN over dt equals to Kn, where n equals to number of viable microorganisms present, t is sterilization time minute, and k is thermal death rate constant, and the unit is 1 per min. According to the equation 1, the negative sign indicates that as t increases, n decreases. If n not equals to initial number of organisms and nt equals to number of organisms still present after a time period of t, actually we can derive another equation which is equation 2. Nt equals to n naught E exponent negative kt. From the equation 2, we can make it into another equation using ln, which is ln nt over n naught equals to negative kt, which is also equals to ln n naught over nt equals to kt. N naught over nt is basically known as inactivation factor. Design criteria which indicates the contamination level of the medium initially present as N naught and need to be brought to a sterility level of NT.
Hi, my name is Nishanti Kumar. My metric number is 216029. Just now we see what is the definition of sterilization. Now we're going to see what is the definition of batch sterilization. The definition of batch sterilization is the reduction of contaminant organisms through the aging of a vessel. Apart from that, the entire volume of media is sterilized at once through the use of thermal or radiation techniques. Some more, when running a thermal batch sterilization, the system goes through 3 steps, which is heating, holding, and cooling. By using Arrhenius equation, we can obtain d ln k per dt equal E per RT square, which we get from the kinetic of thermal death of microorganism. E, which is equals to activation energy in joule per mole, a specific constant for the population. R, which is equals to universal gas constant bracket 8.314 joule per mole K. T, which is equals to temperature in Kelvin. So whenever the temperature is Celsius, we have to change to the Kelvin. Then the integration of equation 5 is K equals to K naught E power of negative E per RT. K naught, which is Arrhenius constant. So in batch sterilization, we want to see a graph. The graph shown in the figure, which is Arrhenius plot. The x-axis, which is bracket on our t, while the y-axis, which is ln k. The y-intercept is ln k naught. Constant k naught and E per R can be calculated by Arrhenius plot draw between ln k and 1 over t. Value of k are evaluated by equation 3 by measuring nt at different time interval. The equation which we get is from the kinetic of thermal death of microorganism. Ln bracket nt per n naught equal negative kt, which is equation number 3. Procedure is repeated at different other t, and the Arrhenius plot is made to make a graph so that we can able to get a gradient slope m, which is equals to negative E per R, intercept at y-axis c, or in y-intercept, which is equals to ln k naught. So the y-intercept, which is ln k naught. Finally, we can obtain the equation from the graph, which is ln bracket n naught per nt bracket equals to k naught t E power of negative E per RT, which is equation number 7 that we obtained from the graph.
Hello everyone, my name is Chitya Bashini, daughter of Chittamurthy, and today I would be talking about del factor that comes under the chapter of sterilization under biochemical engineering. Now, what is del factor? Del factor is also known as delta factor, and this gives a definition of an estimate of relative reduction in the number of living cells with respect to their initial number. Now, del factor can also be calculated by using a formula called as initial number of microbial cells is equals to the number of cells after time t, and this also gives a product of one cell. So from this, we know that del factor has its own formula which can be used in the following question. So in this del factor, the equation 7 acts as the design criterion, which is also called as del factor. And this can be equated into a formula which is also known as ln n naught over nt is equals to k naught t e to the power of e over rt. This would be the equation that will be used in this delta factor. But there's another factor also called as Nabla factor. This Nabla factor is also known as the sterilization criterion. And what is the meaning of Nabla factor? Nabla factor is the measure of fractional reduction in living organisms count over the initial number present. This can be produced by a certain heat and time regime, which is also can be concluded as delta equals to ln n naught over nt, which brings out an equation number 8. And this can be combined into equation 7 and equation 8, which gives out into delta equals to k naught t e to the power of negative e over rt. So when you rearrange this whole formula, it gives you out a product of which involves an equation which is also known as ln t equals to er bracket 1 over t plus ln delta over k naught. Now, when we look into the plot, the graph that we got based on the delta factor that we studied before, we can see the graphs. There are 4 lines that are involved in this graph, and all these lines are straight lines, but they are increasing linearly. Okay, so from this we know that the degree of sterilization delta may be obtained over a wide range of T and T regimes. So this is the graphical analysis of del factor. Now let's look into the practical purpose of del factor. And what is this purpose about? It is a risk factor of 1 out of 1,000 being contaminated. So for example, let's just assume that all contaminants under a single category of spores, which also includes Bacillus stereothermophilus, the most heat-resistant microbial type, which brings out also the activation energy of E equals to 285 kilojoule per mole, which also concludes into an Arrhenius constant, which gives out a K naught equals to 1 times 10 to the power of 336.2 per second. Okay, so from this we know that the formula, it equates into Nt equals to 10 to the power of negative 3, which gives out a delta equals to ln n naught over Nt. So that is the final microbial count in the medium after sterilization should be 10 to the power of negative 3 viable cells. So del factor, if it is unsterile broth containing initially 10 to the power of 11 viable cells, which is also brings out an n naught equals to 10 to the power of 11. So from this, we know that the delta is equals to n ln n naught over nt, which can be substituted with the n naught and the nt, which brings out a product of ln 10 to the power of 11 over 10 to the power of 3. And this will completely conclude into ln 10 to the power of 14, which gives out a value of 32.2. So from this, we know that the overall del factor is definitely 32.2. So from this, we theoretically understand that normally the destruction of cells take place at 121 degrees Celsius, which is corresponding of steam pressure of 15 psig, which is equivalent to 0.1 mn per m square gauge. This period known as holding period, since the medium is held at 121 degrees Celsius. So some cells destroyed during the still build up to 121 degrees Celsius. So in this process, we know that this whole process is called as heating period. Okay, so from this we know that some cells destroyed during cooling period too. Okay, so this cooling period happens from 121 degrees Celsius to room temperature, meaning the temperature will decrease. That's why it is known as a cooling period. So the overall period, which gives up a sum of heating period and cooling period, will hold up into an equation, which is delta overall equals to delta heating plus delta holding, and then lastly with the combination of delta cooling. So this will give you the last equation in this del factor. So this is all about del factor in this sterilization topic, and I hope that people like guys understood everything.
Before this, we went too much deeper into biochemical sterilization theories. I hope by now you would understand and have a basic knowledge about proper sterilization. So now let's look how functions and biochemical sterilization interconnects. The first question we have here is the specific death constant of heating and cooling during sterilization of a medium at 121 degrees Celsius is 0.1 min 91 and 0.2 min 91 respectively. The heating timing is 20 minutes and the holding timing is 30 minutes and the cooling timing is 30 minutes. The decimal reduction time during holding is 2 minutes. The initial batch contains 6 times 10 to the power of 15 organisms at 30 degrees Celsius. Find the sterilization performance at first. Then later on, after part 1, if the power fails after 15 minutes of holding time, for instance, after it reaches 121 degrees Celsius, what will happen to the sterilization if the cooling process is not affected by it? Let's see how functions kick in this equation. Just now we see the question. Now let's look into the solution. Let's see how function kicks in and helps us to solve this problem. So during the holding time, the power went off after 15 minutes, and so the heating stops, and cooling started. So we know just now the time allocated for holding is 30 minutes, and the time allocated for cooling is 30 minutes. Now the 30 minutes for holding will be reduced to 15, and that balance 15 will be added up to cooling, which will make the cooling time by 45 minutes. Now let's find and not holding. And not holding is already given, which is 8.12 exponent 14. This is the constant that we will be using for our functions equation. Our functions equation will be NT holding equals to N not holding exponent negative KD T. NT holding is the present batch of cells. N not holding will be the initial batch of the cell. Exponent to the negative KD. Negative KD will be the thermal death kinetic rate constant, and time will be our independent variable, which is going to alter our dependent variable, which is our NT holding. After we substitute all the numbers into our equation, we will get the final answer for 2.54 exponent 17. This is the NT holding, which is the present batch of holding. The present batch of holding will be the same as the N naught cooling, which is the initial batch of cooling, because it is just right after it will be carried forward. So hence we know N naught cooling is 2.54 exponent 7. Now let's find what is NT cooling, so that we can know what is the last batch of cells that is surviving after the end of the sterilization. NT cooling equals to N naught cooling exponent negative KDT. N naught cooling is what we are going to find. NT cooling is what we are going to find. N naught cooling is what is we already got, which is NT holding. The time is 30 plus 45, as I said earlier. The cooling time will be added to 15 since the holding time is stopped right after 15 minutes, and the thermal death kinetic rate constant will be 0.2. After we solve this, we will end up with 3.13 exponent 3. This will be the surviving cells surviving after the sterilization. Thus, we know that the sterilization is not complete. Thus, this is how we solve this sterilization question with functions. The independent variable will be time. The dependent variable will be the anti-cooling or anti-holding. This is how function helps us to solve by substituting one equation to get a product of another one. Thank you.
Okay, that's all from us. Group 6, we actually take biochemical engineering. So in biochemical engineering, we take the application of sterilization. So we can able to relate the function with application of sterilization, and we also provide a problem and also with a solution that can relate with the function. So I think we can be successfully able to relate with function and also with the application in the biochemical engineering. That's all. Thank you.